All right, hope the screen is visible now. So, welcome all of you. Uh, this is Vijay Rane. I'm a Prime Minister Research Fellow in the IIT Delhi, and today we are here to solve the problem based on the session, uh, based on the the course one and two dimensional NMR spectroscopy for the chemist. This course, as the taught by Professor, and which is based on the fundamental concepts of spectroscopy as well as the NMR determination and some NMR spectral parameter and their interpretation. In the third week, we have seen these are some topics like which include uh, internal interaction parameters that we have already seen in the week one and week two. Later, now in this third week, we have seen the external and internal interaction in the NMR spectroscopy with regard to the chemical shifts, then the NMR spectrum as well as the chemical equivalence. Then we have seen the conversion of the frequency to the ppm. So the frequency in the hertz to the ppm delta values in the ppm, which is like particularly we have seen this formula delta is equal to the shift in the hertz from the TMS, that is the tetramethylsilane from that is internal standard, and with respect to the spectrometer frequency in the megahertz. And later part of the third week videos, we have seen the field dependence and the factor affecting the chemical shifts. So all these topic we are going to cover some problem based on this one. So before going to the problems, I would like to open the session for some questions. So if anyone have any question or doubts regarding the topics, these topics, you can feel free to ask that we will discuss here. So please, if you have any question, let me know. Anyone have any question?
Sir, fifth number question that I am not able to solve.
In the assignment, third week
Yes,
assignment,
yes,
right?
theoretical part, sir.
All right. So the fifth question is like the question I will just write, take this question into the, all right. So this fifth question, and I will not solve the exact question, but I will let you know so you can get the answer of the question. All right. So anyone other doubt regarding any other? So we are going to cover this question when we start the discussion. All right. So this is the one question that we are going to cover. Any other doubt? All right. So if you don't have doubt, we'll move to solve other problems. So yeah. So this question is the question is when the 1H NMR spectrum of the molecule is taken in solvent D2O. So the question itself it mentioned. So let's say we have taken any molecule, any random molecule. Let's take the example of any simple molecule like benzene is taken in the solvent D2O. D2O that is deuterated water, right? So D2O we have taken. The solvent is D2O. One additional peak is observed at 4.8 ppm, right? So this peak can be attributed to. So the option A is A, B, C, and D. There are four options given. The option A is peak from the protonated solvent. The second option is deuterium resonance. The C option is unexplainable impurity in the solvent. And third is peak from 100% deuterated CdCl3. So in this question, there is nothing to do with any CdCl3, right? Because we have taken the NMR in the D2O. So our solvent, when we fill the NMR tube, we take the sample and we take a few mg of compound, let's say 3 to 4 mg compound we have taken. In this case, we have taken, let's say, benzene. and the solvent we have used for this one. So we have added about 600 microliter of the T2O, right? So this is the case, and the question itself it mentioned we observe one extra peak at 4.8 ppm. So where this 4.8 peak came from? So benzene, let's say the benzene proton came at I will just put any arbitrary value. I don't know exact value of this the proton, but let's say in the benzene there are proton they came at the delta ppm 4.7, right? So the benzene all seven protons are equivalent. That we have already seen how these chemical equations. Also, we are going to solve some problem based on this. But for now, let's say take example. It shows only one type of protons, and there are six hydrogens. So they all are chemical equivalent. So and they resonate at 7 point. They show the delta value 7.4 ppm. Now the where this 4.8 come from? So we have taken D2O solvent, right? So what happened? There are in water H2O. We have replaced this H2 by D2. So this there is also deuterium. Here again another deuterium. So there are two deuterium in this molecule, and this is oxygen. But there are some chances. Only one of these deuterium is replaced, other remain intact. So it might be DH. So how it will be? It will be DOH, right? Or HDO. So this is one molecule. This is one possibility. Or another possibility is H2O, and our the other is the D2O. That's already our solvent. So let's say there are some impurities of DTO is present in the solvent that will be in the form of maybe water, H2O or HDO. So in which the only one deuterium is replaced and one is hydrogen, one remain intact there. Here both the deuterium is mm, none of the deuterium is replaced. So let's say there are 100 molecules of this deuterium in this solvent, but only the 99.9% deuterium, right? D2O we have, but there are some 0.01% this type of impurities are present, like HDO or H2O. That impurity shows the peak about 4.8 ppm. So the answer is like peak from the protonated solvent. So this protonated solvent is the solvent is D2O, right? So it will be these two are the possible protonated solvents in which the one proton or the two proton, both the proton from the solvent are the hydrogens. So they are NMR active and they show the peak at the 4.8 ppm. So the option A is the correct option here. The peak from the protonated solvent. This is not the detonator readiness. Unexpected infinity is also wrong. The peak from 100% CDCl3. It doesn't have anything to do with the CDCl3 because our solvent is D2O. So alright, got the answer?
Yes, sir.
Yeah. So I will tell you one more question regarding the same one. So I think I have taken one more question similar to this one also. So that we will discuss first, as since we have already started this topic. All right. So this is another question, very similar. Now you have to tell what is the correct answer here. So the question is, when 1H proton N1 spectra of the molecule, any molecule, is taken in the solvent CDCl3. Now here the similar question, we have taken the NMR in the CDCl3. So CDCl3 is our solvent here. It shows yeah, the NMR spectra shows 7.25. One additional peak at 7.26 ppm is observed. And now we have to tell where this peak come from. So what is the structure of this CDCl3? One is the deuterium, and there are other three chlorines are attached, right? And what are the other possible impurity present in this solvent, which is CHCl3, right? So because of this hydrogen, the 7.26 show the impurity peak at 7.26 ppm. So here option as like prior, which option is correct here? There are four options: A, B, C, and D. So here which option is correct? Uh, this one, the peak from CHCl3. This is the correct option here. CaCl3, or we can also say the protonated solvent as like by your example. So it might be the is this also can be mentioned in this form like peak from the protonated solvent. Protonated solvent means the whatever solvent we have taken, the CdCl3. So what is the protonated form of this CdCl3? It might be the CHCl3. That is, deuterium is not replaced by the deuterium. Instead of deuterium, there will be hydrogen. So as prior mentioned, although there are very uh, uh, percent this CdCl3 is present, but there are some small amount of in the order 0.001% also uh, that also shows in the you can observe in the NMR spectra. So because of this, we observe one peak, extra peak when we take this NMR in the CdCl3. We observe 7.26 ppm. There is one sharp peak in the NMR spectra. Right? Got any doubt regarding this one?
No, sir.
Yeah. So you got the answer definitely, right? All right. So we'll move for the next question. So this is the one question, which is the in the maybe the later part we have seen the chemical equivalence. So here the question is the molecules we have given three molecules, and we have to mention in the molecule low structure is given below the number of distinct chemical shift expected in the proton NMR spectra. All right, we have three examples, and you have to mention how many distinct chemical shift are present in these three molecules. So here it will be hydrogen, right? Here also there will be hydrogen. So anyone have any idea how many number of
Two,
peaks?
two pigs.
All right, one option is two. Any other? What is correct option here? Two, three, four, five. So which option is correct here?
Option third. Option B, 3 peaks.
Uh, option third or three number of peaks?
Option B, 3 peaks.
Yeah. So three peaks here correct option, because if you look at this molecule, there is a plane of symmetry present in this molecule, right? So if you pass this plane, so this will be A, let's say. This is also HA. Again, I will take some different color. All right. So this will be the, let's say, this will be HB, right? This is another type. And another one is this one. So these hydrogens are distinct. So these three types of protons are present. So that's why option option B is the correct option, which has the three distinct number of protons present here. Similarly, next question, 3, 4, 5 and 2. So which option correct here? So this is the structure, another structure, and the same question, how many distinct chemical shifts are expected throughout this molecule? Any guess, any idea?
Option D.
5.
All right, so option D, most of people mention option D is here. All right, so I will just mark, let's say this also you have to consider, right? So these three protons will be the equivalent. So this will be 1, this is 2, this is 3, this is 4, and this one is 5. So 5 distinct type of protons are mentioned here, right? So option D is correct option here, right? The next question is the same. We have given one structure, and here how many distinct protons are present? There are 6 hydrogens, and how many distinct chemical shifts are present in the 1H NMR spectra? So anyone?
1.
Right. Here the one option is correct here because all are equivalent. So all are like this identical, right? So that's why it will show only one chemical shift value, distant chemical shift value. All right. The next question is two peaks are detected in 1S spectrum at 400 megahertz. The peaks are separated by 4 ppm, right? So what is their separation in 800 megahertz spectrometer in frequency? Frequency means we have to mention it in the hertz. If it mention in ppm, then we have to consider that into ppm, right? It's already in delta value that we need to consider in ppm. So now we have to give in the form of frequency. So as we earlier seen this equation, I will just take this equation there as well. Control C. Right. So this is the equation we have. So this delta value in ppm. So delta value in ppm is equal to the frequency in hertz divided by instrument frequency in megahertz, right? So we have given two peaks are detected in the 1S NMR spectrum at 400. The peak separated by 4 ppm. So we'll put the value as it is 4 ppm, which is a, we have to calculate the value in for the 4 ppm. They have mentioned this in 400 megahertz. So let's calculate first for 400 megahertz, right? So how it will be? This will be, let's say, x. So 4 multiplied by 400. How much it will be? This x in hertz, which will be 600, right? This is for 400 megahertz. Am I right? Now just calculate in the same manner for 800 megahertz. So the delta ppm will be the remain constant, right? Because it is in the delta value, it will be remain constant, this 4. And for 800, it will be divided by 800. So just multiply by 8 multiplied by 4. How much it will be? 3200 hertz. Are you getting the point?
Yeah, sir.
Right. So here the option A is the correct option here. So you have to keep this formula, remember. So this is the important formula. Remaining the problem based on this one, you can easily solve them. The next question is, in the 1S spectrum, uh, two groups of the group, two peaks are observed respectively at 1 ppm and 2.2 ppm. So let's say this is the TMS, it will be at 0. At 1 ppm, one is there, and another is at 1, 2, 3. So here one peak observed, and here also one peak observed. The intensity of this peak are 3:1. So let's calculate, let's check, just given some random frequency just to the peak intensity 3:1. The most probable assignment for this one. So I will mention here some options I will give here. CH, CH2. B option is OH and NH2. C option here is like CH2 and CH3, and fourth option is CH3 and CH2. All right. So which option correct here? Someone mentioned option C. Any other?
Option D.
Right. So option D is correct here. because they have mentioned intensity, which is 3:1. Always keep remember. People always do the mistake in the hurry because uh, here it mentioned 2, here mentioned 3, but this ratio will be how it will be. It will be 2:3, right? Because respectively it is mentioned, but here 3:2. So option D is correct option here. Also, why this one? Because here there are 3 protons and here there are 2 protons. So the ratio obviously it will come at 3:2. So that's why the option D is correct option. In this way, you can solve some. There are some questions given in the assignment. You can easily select the correct option based on this problem. All right. So the next problem is in 600 megahertz spectrometer, nitrogen 15 resonate at 16.69 ppm. Two peaks were observed in 15 nitrogen spectrum, separated by 30 ppm. What is their peak separation frequency? Peak separation frequency, that is, we can say frequency, that is will be in hertz. So how you will go calculate this one? So I have purposefully keep this table here just to show you some correlation. So here, as we know, let's say we have the 1H NMR that we have taken under 200 megahertz NMR instrument, but it will not. So the instrument will be the same, but for carbon it will be 15 megahertz. Similarly, for nitrogen it will be 20.35 megahertz. So this will be uh, the resonance the resonance frequency values in megahertz of different nuclei, magnetic nuclei. So let's say we have one constant NMR instrument, 500 megahertz NMR instrument. So for our 13C, on the same NMR instrument, we write, if you've seen some papers, it is general mention like the 13C values that 125 or maybe sometime 126 or 125. Then there will be the same the chemical shift values. But for the same compound on the same instrument, the 1H values will be on 500 megahertz that you may generally found. So this is because these relations, because the diabatic ratios are different for these nuclei. So that's why these are the some relations. So let's say they have mentioned 600 megahertz instrument 600 megahertz. So this is generally for hydrogen. It will be same for hydrogen, but for nitrogen 15, how much it will be? So you can just take some simply ratio from here. 200 divided by 20.35. How much it will be? It will be around 10, right? We'll just calculate some approx values. It will be around 10, right? So similarly for 600, this is for hydrogen. It will be around 60 for nitrogen 15, right? So for nitrogen, it will be nitrogen 60. So delta ppm values is equal to what do we write generally here? The frequency, right, in hertz divided by the same equation that we have used prior. And the distributed frequency here for this one will be the 60. And how much delta ppm value they have given? It is given 30. So I'll just rub this one. So just calculate here 30 multiplied by 60. How much it will be? I'll just make a quick calculation. It is around 1800, right? So what is the nearest value here for around 1800? Here, this is definitely wrong answer here. This is 24. This is also wrong. This is 200, and in this one, if you calculate, put accurate value, then you will get the exact answer. This answer will be the correct option here, not this one. Although we have just did the rough calculation because we haven't taken accurate ratio of this one. But the option C, if you just calculate this calculation and use that calculation, it will be 54 around or 56 something, and put here 54 point something, right? 54.5. Then you will get the value. Any doubt here? Anyone have? You can interrupt me in between if you have any doubt. We will discuss that doubt. No, don't hesitate to ask any question.
Sir, I am not understand that clearly.
All right. Yeah, we'll again see how it is. So you know barometric ratios for proton carbon are different, right?
Yes.
And generally, the barometric ratio for this yeah. So this is the one, the plot, sorry, chart we have. So this chart uh, is for the resonance frequency in megahertz of different nuclei in different magnetic fields. So let's say we have some instrument, NMR instrument. So I will take the example of this 500 one, and this NMR instrument is 500 megahertz NMR instrument, right? But this 500 one is 500, that is 11.74 Tesla. This will be in Tesla. If you calculate this one, it will be in 11.74 Tesla. So that part no need to consider, but only keep consider this 500 megahertz NMR instrument we have, and this 500 megahertz, this magnetic field is direct. It will be generally for 1H. It is not for for. So 1H nuclei we have, let's say we have some compound which has nitrogen and some aryl group or any group. For if you are taking the proton NMR spectrum, for proton NMR, that magnetic field, how much magnetic field applies to the proton nuclei, it will be 500 megahertz. But let's say if you are running some other experiment, which like 15 nitrogen 15, right? So at the time of when you are taking this nitrogen 15, this experiment, as like we taken the 1H NMR, it will be a nitrogen 15 NMR. At that time, this nitrogen nuclei will have the experience magnetic field that will be only 15.7 megahertz. It will not 500 megahertz. It will be 15.7 megahertz. This is because difference in barometric ratio, as well as there are difference in the other parameters as well. So that's why this table they have it is given. So based on this table, let's say you can simply check this for 500 megahertz, right? 500 megahertz 1H. How much it will be for nitrogen? It will be only 50. So I have just taken simply the ratio of this one. So how it will be? 500 divided by 15.7. How much it will be? It is approx 10, right? Make it simple. It will be approx 10, right? So it is 10 times smaller for nitrogen. Similarly here, what we have given? We have given 600 megahertz NMR estimate. So this 600 megahertz instrument, how much magnetic field the nitrogen nuclei will get? Only 10 times smaller, right? Because it is, you have ratio check here, it is about 10 times smaller. That is 16 megahertz. So for nitrogen, it will be only 16 megahertz. How that much only the magnetic field the nitrogen nuclei will experience, right? So that's why the instrument frequency in this calculation for the delta, it will be only 60, and the frequency here that anyone and here not given, that we have to calculate, and this delta value they have given, that will be that is as it is 30 ppm. So I have just did the multiplication, so it will be 60 multiplied by 30, so that's like around 18. So let's 1800. So that's option is the correct option here. So if you keep this chart, remember approx ratio. Let's say we have some example for the carbon. So let's take example of carbon. The carbon have how much it is in the ratio. So this, let's say 500 and 125. That is this ratio it will for the carbon. How much it will be? It will be 4. So this 600 for hydrogen. But for nitrogen, how much we have just calculated? It will be 600 for hydrogen. The same instrument given for the nitrogen, only 600 megahertz, and for carbon, it will be only 150 megahertz. So instrument is the same, but this much amount of magnetic field that nuclei will experience in the instrument. That's the ratio. That's the parameter. Sorry, the ratio here given in this table. So here you can see they have shown multiple examples here, 1, 2, 3. In all, it will this ratio will be constant. If you ratio of this 200 divided by this one, this will be remain constant. So this is this megahertz in our instrument. So 500 for carbon it will be 125. On 400 it will be only 100. For 200 it will be only 50. This is 4 times smaller, right? I mean in the ratio of 4. So we have 400 mega in our instrument. For 1H NMR, it will be 400, but for 13C, it will be only 100 megahertz. That's why here also we have taken only 60 in the ratio. So we have taken the ratio, this will be in hertz, 60 megahertz we have given, and we just deal the multiplication, 60 multiplied by 30, it will be 1800 approx, and that will be the correct option here. All right.
Yeah, sir.
All right. So here is some other different type of questions, which is like based on some our actual NMR spectra. So we have some NMR spectra. It will be, let's say, 0 TMS peak, and here it will goes to up to, let's say I will just plot up to 10, and there are in between some delta values 1, 2, 3, 4, 5, 6, 7, and other, right? And the question is given: a molecule has proton attached to very strong electron donating group. Electron donating group. I will just write simple electron donating group. Where is the possibility of locating the peak? So let's take the example. We have CH3H. Similarly, CN, or just skip this example for as of now. We have CCl3H, or we have CBr3H. Right. So we have 3 examples. 1, 2, 3. So, and only focused on these proton values. So what will be the trend here? I mean, this CH3 proton, where it belongs to? This seed, this one, and this one. So what is approx? What do you think the region where it will be lie? So let's say we have this methane.
Methane high frequency region.
Here there is like some sort of uh, what you can say, the confusion between the frequency and shielding that we need to consider. So for that, I will just show some slides here before solving this question. We have some. I have kept some slide here. Yeah. Are you able to see the screen? All right. So this is our general spectra, right? So we called from this region the initial. This will be, let's say we have the peak here that due to the tetramethylsilane, and here it is like the plot just plot, right? This is just axis, and we have some peak here, TMS peak. So this region we called it as upfield. Also we called it as a shielded region because the electron density is higher for this. Uh, the peaks that showed up here, they have the very shielded and also low frequency. Similarly, this side, if you have some electron withdrawing group attached, they goes to the downfield, or we can also mention it as a de-shielded one region or high frequency region. So this concept you need to consider the high frequency, low frequency. Also de-shielded, here it will be shielded. It will be downfield here. This side it will be upfield. So now your answer remain the same or opposite? So the question is, we have some
Opposite, sir.
right. So this low frequency means shielded, right? So we have any strong donating group attached. So where it will go? So it will go this side, right? This region, let's say A and this B. So it will go in the A region, that is upfield, shielded or low frequency. If you have strong electron withdrawing group attached, now what will be? So let's example have CHCl3, where it will go? It will go in this region because it is withdrawing group attached, right? So it will go in the downfield or the shielded region or high frequency region. Here, example of CH3H, that is methane. I just isolated this hydrogen. The methane it go here. So in this manner, if you have strongly donating group attached, then it will go to the upfield or shielded region or low frequency region. And if you have strong electron uh, withdrawing group attached, like the chloro, bromo, or fluorine attached, at that time, where it will go? It will go to the downfield, right? Hope this will clear. Now take some examples here, upfield and downfield. So we have some like functional groups here that we have shown here. Let's say we have functional group. Let's take from here. Alkyl. Alkyl, what are the examples of alkyl? Like let's say methane, CH2, CH3, and this side it has again CH3, propane, right? Or this is cyclohexane. This kind of molecules, they lies all these protons lies here in the upfield region. Also, there are some examples like if you slightly move from 1 to 2, there will be some ketones, CH3. Either this side you take just R and just consider this hydrogen. So this lies between 2 to 3, right? So this ketone. Again, if you have alkynes, so alkynes lies here in between 2 to 3 or sometimes 3.5, 2.5 to 3.5, this region. Also, if you have some example like here, C, H, and here X is attached, let's say OH, oxygen, or fluorine, or bromine is attached, then at that time, let's take example CH2, CH2, Br, right? So this CH2, these hydrogens, which is in the highlighted in the blue color, they lies in between this one, in between this 3 to 4 or sometime 4.5. It depends on the how electron withdrawing group is attached. Let's say bromo here, right? When there is a fluoro, at that time it will be lies slightly in this side. When there is oxygen, it is slightly electron deficient. Sorry, not that much electron withdrawing than the fluoro. At that time, this will lies around 3.5. In this way, this strain goes. Again, we have some olefins, alkyne double bond, right? So this hydrogen double bond hydrogen, any example like any kind of example, this hydrogen, let's say here R is attached, here R is attached, here R attached. So this hydrogen, where it comes, it lies in between 4.5 to 6.5 or sometimes 7, depends on the what are the R is here. So if the electron donating R at that time, uh, this region, when there will electron withdrawing R group is there, so that time this region. So in this way, the these chemical shift values are slightly moved from in this particular region. again move in the aromatic region. So this region from 6.8 to 8 or sometime 9, this region we call it the aromatic region, right? And so aromatic region, that we know there will be a benzene ring attached, and whatever group attached depends on that these protons will fluctuate their delta values. So if R is equal to OH, then it will be this proton pair, it will be nearly near to 7. When R is equal to fluorine or nitro, at that time, uh, for this proton's value, it will be 7.5 or 8, around that one. So that's why you have to at least keep some this type of some region noted, so you will easily found out where are the actual where are this proton will belongs to. Again, move to the region like 8.8 to 10. There will be aldehydes. These aldehyde protons, they showed in between 8.8 to 10. And there are some protons like carboxylic acid protons. They goes to beyond 10. So carboxylic acid, they goes here. So generally we know carboxylic acid, how it is presented. So carboxylic acid, let's say it is like here, and this O, this H, right? So you know, right? This is how the carboxylic acid are present generally. They form hydrogen bondings, right? So that's why these protons are very much de-shielded compared to the other alcohols and other any other groups. So that's why the carboxylic acid protons are like beyond this one, beyond 10. So this region is downfield region. So this region we call it the downfield region. This is like upfield. So comparative we can say. Any doubt here? If you have doubt, please ask you. Otherwise, your doubt will not get clear. If you have because later part of this course we are solving actual problems, and also I will show some raw data, NMR data that will process here in the session itself. Here are some examples again, uphill, downhill, that just given in some different manner. So this methyl protons show nearly 1. This methyl attached to the ketonic group about 2.5. The chloro, let's say chloro, any halogen compound attached, it show nearly 3.5. Or else we have some alcohols or anything, or ethers, they show here. And in the let's say the very highly electron withdrawal group attached, let's say fluorine, then it goes to 4.5, nearly 4.5. So this how the uh and they comparatively we call it as like these are, if you have, if they have given any comparison between these 5 molecules, for comparison purpose, we call it as a upfield proton as compared to other, and these are the downfield protons compared to this side, these other protons. So upfield, downfield, they are like comparative concepts. So comparatively, let's say we have given the methyl, and comparatively these two, and we have to given, let's say this is A, this is B. So AB. So which is like uphill, which is downhill comparatively. So comparatively B is uphill than A. So that's how we have to mention. So like this one, right? So if you have given a comparison of these two or these three, then we can say these ether protons are comparatively downfield than these halo compounds, like this way, right? Hopefully this concept will get clear here. Now here one example. So what it is, as mentioned, very simple example. Here it mentions like a molecule has a proton attached to the strong electron donating group. Electron donating group. So where it will be? It will be in the low frequency region. And any other option is correct here? Low field, high frequency region. This is obviously wrong. Less shielded region, wrong. No peaks will be detected from proton. That's wrong. Low field, as we have already seen here. This one, right? This is upfield. This is downfield or low field, right? So option, this one is correct option here. Low frequency region is the correct option, or upfield also if they have given some upfield, high shielded region. So in this way, you can solve the problem based in which is in the assignment. So the simple problems here. So I think uh, here's one more question, which is generally based on the how many different type of protons are present here. So you can easily solve this problem. I don't think there is any uh, difficulty in solving this problem. So here, this methyl, this will be one type of protons, and this one and this one, this will be the second type of proton. This is again third type of protons, and this one will be the fourth type of proton. So here there are four different type of protons present. Similarly, in this one, there will be one, right? Only one type of protons are present. Here, if you just check here, so 1, 2, and 3. Three different type of protons are present. Similarly here, this will be CSE right here. So 1, 2, 3, and 4. Four type of proton. Sorry, three types. So in this way, you can solve this problem based here. So anyone have any doubt here regarding the any topic that covered in the third week?
Sir, one question number 8.
All right, we'll go to the question number 8 from the assignment, right?
Yes, sir.
All right, here, all right, I think I have given this, yeah, we are going to solve similar question like this one, not the exact same. All right, so here it is the same question. I'll just put some slide. All right, the question is the 1H peak are the two 1H peak. Let's say the peak A and peak B are separated by 1000 hertz, right? The separation here is 1000 hertz. So this separation on 500 megahertz. Instrument, right? The peak separation measured in ppm on 200 megahertz and 400 megahertz, 200, 400, and 600 megahertz respectively. Peak separation in ppm. All right. So I think you should not have any doubt regarding this one. But all right. So we have one formula, the same formula that we have solved used by prior. The delta in ppm is equal to the frequency, right, in hertz divided by the frequency of instrument in megahertz. It is given. So this delta is constant. It doesn't matter this frequency, whatever this frequency is or this frequency is. So this frequency X and this Y. This Y is for instrument and X is for the peak separation frequency and the delta value. So I think I should take the answers from audience. Anyone have any answer here? All right,
Sir,
we'll
2
solve this.
ppm for all.
All right, 2 ppm for all. Yeah, this is the correct option because this delta is constant. Or else we can just check whether it is remain constant or not. Just check the value. This delta ppm, this X, let's say we take the X and just calculate in 200. So on 200 megahertz, how it will be? On 200, it will be, oh, but this delta, yeah, the delta, every time that delta value, that will remain constant here, right? So this one, where it is, delta in ppm. So that takes, we have to calculate first for this, whatever the given data. So let's take 1000 divided by 500. So this delta X will be the 2 ppm, right? 2 ppm. and just keep that 2 ppm value. So that's what the 2 ppm, that's the correct option. It doesn't matter whatever this frequency is, because this is the ratio, right? And this ratio delta ppm value will remain constant. It doesn't matter if you take the NMR in 400 megahertz, 500 or 600. Every time you get the similar spectra, similar in terms of the delta values. This coupling constant values in the hertz will change, but this delta value will remain same. Based on this one, I will just uh, solve another problem. It is very, very similar to that problem. Yeah, this is the one now. Now the same question is the two peaks, similarly as seen this prior problem, the two peaks are separated by 300 hertz. Sorry, 3000 hertz. So they have given two peaks and which are separated by 3000 hertz on 600 megahertz instrument. Their peak separation measured on 400 and 500. So they have given peak separation on, sorry, here the ppm value I have forgot to put here. So let's take for simplicity any peak value, like let's take 2 ppm. The delta value I forgot to put here. So two peaks they are given, which is separated by 300. Sorry, ppm value that we have to calculate, right? From here, we can get it from here as well. 300 hertz on 600 megahertz instrument. Their peak separation on 400 and 500 that we need to calculate. So let's calculate for the first delta value for the given one. So delta value for given one will be 3000 hertz divided by the 600 megahertz, right? So the delta, how much delta it will be? 1, 2. This will be 5, right? 5 ppm. So delta is equal to how much? 5 ppm. Now we got the delta value. Now we have to calculate this peak separation frequency. Which one? This one. How much for on 400 and how much on 500? So similarly, we'll put delta we know, right? So 5 is equal to this delta in hertz value that we don't know. And on which instrument, let's say calculate for the 400 megahertz instrument. Let's calculate for 400 megahertz instrument. So how much it will be? 400 multiplied by 5. It will be
2000.
2000 hertz, right? Similarly, for on 500 megahertz, if you want to calculate, so that time, how much it will be? So just do multiply 5 multiplied by 500. So how much it will be? 2500, right? Hertz. Right. Hopefully you got the correct option is this one, 200 and 500 megahertz. So right now, I think hopefully you got the answer for the prior problem as well as this problem as well, right?
Yes, sir.
Yeah, this is how you need to calculate. The delta ppm value, delta in ppm value will remain constant regard of any NOR megahertz instrument you use, but the delta value in the ppm will remain constant. But delta value in this frequency, the peak separation frequency will change. So that's the reason to get the highly resolved spectra, we generally do the spectra in the higher megahertz spectrometer instrument. So higher megahertz, let's say 600, 700, that megahertz in one instrument will be good, give very good quality data rather than the 300, 400 or 200 megahertz in one instrument. So this is the one problem here. So let's take one we have a peak which is value in the delta. Let's say this is at 3.5. Here also this 3.5 value 3.5, that one will not gonna change. This will also that 3.5 will remain same. So delta value will remain constant. But if you take the NMR in the 300 megahertz instrument, we get this splitting or the separation between two peaks only 15 hertz. But if you do the same sample on 900 megahertz instrument, this peak separation will be 45 hertz. Got the point? So you have to keep consider this formula. This is one of the important formula, and based on this formula, you can solve any kind of problem. Also, there are some concepts in this topic that we have covered. What is up downfield? What is upfield? Again, the chemical equivalence, that sort of protons. What if you have given any complicated example? Let's take example of this chair and board form of this one. So what are the which the protons are chemical equivalent, which are non-equivalent, that you should able to solve. These are some higher problem. This the based on stereochemistry, but yeah, but for now, let's say the simple problems like OCH3, and here there is NO2. So you should able to give the answer how many different type of protons are present here, that kind of. So I think that's all for today. If you have any doubt, please let me know. Then we will discuss here also. Anyone have any doubt here? In this week, there are simple problems, not much complicated. So from here, I think we are actually starting the our NMR spectroscopy, and yeah, hopefully you will enjoy this topic. If in the next 3 4 again other week videos. So if you don't have any doubt, I will stop here. Thank you so much for joining.